Hey, hello there. This week I will be practicing solving problems on the topic of binary search. So since this is Monday, I'm doing a really quick review on these topics. So this is a really fundamental questions, techniques in computer science. I imagine today is going to be really short. So binary search is the method we can apply to efficiently find the target value within a sorted sequence. So a non-binary search method of achieving the same goal is to just check element by element in the sequence. It will be linear time because in the worst case, we have to go to the very end of the sequence to find the value. And the problem with this brute force checking value by value is that it does not utilize the fact the elements in this sequence are sorted. So if we just randomly pick a number inside the sequence and compare that with the target, if the random number is larger than the target value, we know that the target is in the smaller part of this sequence. If the random number is smaller than the target, then we are sure the target value is in the larger half of the larger portion of the sequence. So binary search is basically just applying this logic. So we maintain a lower bound and upper bound of the search space where the target is sure to reside. The search space initially is just this full sequence. And in each iteration, we try to update either lower bound or upper bound. And we do so by taking the middle element in this current search space and compare that element with the target value. And just based on whether this middle element is larger than or smaller than or actually equal than the target, we can decide whether we chop the search space into half and take which half, whether it's from lower to middle or middle to upper. Or if we just successfully find the target, we can return. So as a matter of fact, we are reducing the problem size by half in each iteration. That says the worst case runtime for binary search is in the log time. And I guess another thing to realize is usually in the simple use cases that we have array that's a form of the sequence, and we want to find an index for a target value. So we'll search on the index accessor for the values in this array. So it can be actually slightly more than complicated than that. We search for maybe a domain of a function, and we need to find a target value in the codomain. And since the function is monotonic, meaning that when we map order the number in this domain, the range are also sorted. So this I think it usually happens in a little bit more difficult level kind of binary search. Not so straightforward questions that can involve binary search. Usually in this kind of format, there is not a very physical upfront sequence in there ask you to search. But when you analyze the problem, you might realize, hey, this question is monotonic. This function, there is a monotonic function that we can utilize the binary search to help us find a value in the domain. That when you map the value into the codomain, map the value into its value in the range, we can do a comparison and using binary search. So let's just be aware of this. Sometimes it's important to realize that certain question is actually can be translated into this kind of formulation and be solved with binary search. And very lastly is sometimes the sequence as a whole may not be ordered, but there are certain parts of it is ordered. And if we can identify whether the target is in this part or not, then we can apply binary search on the subsequence. So this is also something we should look out for when we think about things related to array or searching something in a sequence. So that's some a few remarks that I can think of about binary search. Then it's some code examples about. I have 3 different versions of binary search. The first one is to find a value. So given a sequence, here we have an array and target value. the lower bound and upper bound initially is 0, and the very last element in this very last index in this array. We could also set this to as default and allowing some kind of prior knowledge ingestion. Maybe we just know the lower bound and upper bound of this question, so we don't actually have to go so broad. If we have some other knowledge, we can actually throw some two more parameter here. But basically, the routine is while the lower bound and upper bound has not meet each other, what we need to do is to take the middle point. In Python, integers can be arbitrarily large, so you can just add them and divide by 2 and take floor. But for non-Python, I guess you could do low plus high minus low to avoid these two numbers add together being overflowing. But for Python, this is fine. Then we're just gonna compare the middle element, which we can access by ARR brackets n. Compare that with the target. If we find it, we can return that index. Otherwise, based on the relationship between this element and the target, we can update the lower bound and upper bound accordingly. Since here we already excluded the case the middle element is equal to the target, we can we can drop the upper bound to be middle index -1 and lower bound to be middle +1. The case that will be the reason that we have an equal sign here is to allow this while loop to exit. So if we couldn't find a value in this sequence, then if we don't have this equal sign, we might be locked in this while loop. So once we exit this while loop, meaning we did not find the value, we can return something like null pointer or none, or things in that nature. Since we are looking at a sequence which might be 0 index, that we can return -1. That's perfectly fine. And this is to find a value. A quick note is if there are multiple occurrence, duplicates of the same element, this code here will find the index for that value, but it's not guaranteed it's leftmost or rightmost. Sometimes the problem will ask us to find the first occurrence of a certain number, so this code wouldn't solve that problem. And just to reinforce the point here, we can apply binary search on the domain of a monotonic function. Sometimes the condition here is we don't actually have an array, but rather we can define a function that takes a number, and by calling that function we can determine whether we want to have the high or have the low. So that's just some question might not be in this kind of a simple, straightforward format, but have you to interpret the question and code that function, and instead of directly accessing the element to tell us direction, we actually should use the function call to give us direction. So that's the first version of binary search. And so sometimes we need to find the first occurrence of the target value. We can use this format, which is initially the same. The middle point is the same, and as long as the middle value is smaller than the target, we increase the lower bound to be middle +1, and otherwise we reduce the upper bound to be this middle point. And the termination, the while loop has a termination criterion of low less than high. So when they exit, low and high will be equal. So we can return either low or high in the end, because they're going to be equal after the while loop. So even though I put low here, either one of those is the same value. The reason it works is this is gonna guarantee that low is going to be the first element that's equal to or larger than the target. So if you just look at this condition here, it tells you that as long as the element at the middle is lower than, strictly smaller than target. We want the low to be at least a 1 plus to that. So in the end, the low will be pointing to the first element in this array that's equal to or larger than the target value. So that's depicted here. If it returns the index I, then array from the first to upon until I, just immediately before this I element, it's going to be all smaller, strictly smaller than target. And the elements in this array from and include this I element, it's going to be greater than or equal to T, the target. So if the element does exist in here, then I is going to pointing to the first occurrence. In the case that the target value does not exist in this sequence search space, then the index return is going to be the first element that's just ignore the equal. It's going to be the first element that's larger than the target. And the alternative kind of the code is to find the rightmost occurrence of the value. So if we have duplicates, this finds the last occurrence of that value. So the code is as follows. The stuff is pretty much the same, except we put a equal sign here, and we return left subtracted by 1. So here, just looking at this condition and this update rule, it's saying that the lower has to be strictly larger than T. So when it's terminated, we return the lower subtracted by 1. So if this value does exist, L is going to be the last occurrence. If it's not, it's going to be the last element that's smaller than the target value. So that's summarized here. And actually in Python there is this built-in module called bisect. The bisect left, it's pretty much what this binary search left is doing, and the bisect or bisector right it's returning L instead of L minus 1. So I guess the reason is that if we return L rather than L minus 1, this sum right here will be array from 0 towards L will be towards I will be less than or equal to T, and array from I and on will be larger than T, which will be pretty much this, except move the equal sign from the latter to the formal. So it will be more aligned between this understanding about left and right, how that separated this array into two halves. But here, usually when we apply binary search with a target value, we are looking for the in this kind of fashion, we are looking for the last occurrence. So that's why I'm returning L minus 1. So this code can be quickly modified to be the return L that will result in this code to find the location where we can actually insert the value that does not change the order. Right now with this code, if the elements does not exist and we insert the target value in that location we found with this binary search right, it will violate the sorted order. We need to do a one-time swap to correct that, or we just modify this code to return L. So there are 3 variants that I use and I memorized. So just gonna see how this can be applied to solve problems. Yeah, that's really it. As usual, the documents is gonna be on my GitHub repository. So that's it today.